Hello and welcome. In this video I want to take a look at some properties of line integrals of vector fields along curves and then take a look at one example. So let's start here with some properties. Suppose capital F and capital G are continuous vector fields with domains that contain the oriented smooth curve C. Now it occurs to me as I say that I haven't mentioned the word oriented yet in any of the previous videos. And an oriented curve would be one that has a direction. I mean, you can think of a curve as just a set of points in the plane or in space, depending on which one you're in. But to say it's oriented is to say you've chosen a direction to move along it. Right? It's not just a static set of points, it's a path that has a starting point and an ending point. Now, each curve, of course, could have two orientations because you could traverse it one way or you could traverse it the other way, and you've just chosen one. Essentially, you've got it parameterized so you know which way you're moving across it. Okay. And of course, to say smooth, that means it has continuous first derivatives. So here's some properties. The line integral of the sum of the two vector fields dotted with dr is equal to the sum of the individual line integrals of the vector fields dotted with dr. So the integral of f dotted with g dot dr is the integral of f dotted with dr plus the integral of g dotted with dr. Okay. And number two, the integral of k times, where k is a constant, a real number, k times f dotted with dr equals k times the integral of f dotted with the dr. So these first two, if you've had linear algebra before, you may recognize them as the two linearity properties. The first one's quite often called the additivity property, and the second one is called the homogeneity property. So line integrals satisfy additivity and homogeneity, which means that this operation of taking vector fields and doing something to them and ending up with a number, that I guess you could call it an operation, or maybe it better is transformation. It is a linear transformation from the space of vector fields to the space of real numbers. Okay, that's kind of nice. If you got a linear transformation, there's a lot we know about the properties of linear transformations. Okay. Now, third property here is that if I integrate this f dotted with dr backwards along C. So I've chosen an orientation, say it starts here and ends there. So minus C would be the one that starts here and ends there. And so if I integrate backwards along the curve, then I get minus what I would have had when I integrated forward along the curve. Now this is different than what we saw with line integrals of scalar functions. The thing is, with the scalar function, you used the speed. The speed was part of it, the length of the velocity vector. And that was always taken as positive. And so it didn't matter which way you traversed it, that was positive. In this, because that cancels out, right? Because we had a unit tangent vector, which was r prime divided by the length of r prime, but then it was times ds, but the ds was the length of r prime times dt, and so the lengths of r primes canceled out. And now we do have that information about positive and negative going forward or backwards along the curve. Okay. Number four, if C, up here we assume that C was a smooth curve. I'm going to change that now to say, assume that it's just piecewise smooth. Right? That is, C can be written as a sequence of curves, C1 plus C2 plus C3, where each of the CIs are smooth curves, such that the endpoint of CI is the start point of CI plus 1. So you move along C1, and then maybe you take a sharp corner, but you start here and then move along C2, and then maybe there's a sharp corner again, and you move along C3. So this would allow C to be not smooth everywhere, but at most a finite number of points where it has a sharp corner, right? Where it's not smooth. But in between those sharp corners, it is smooth, right? So those are the smaller pieces. Then we can say that the integral, the line integral over the whole curve C of f dotted with dr is the sum of the line integrals over the pieces. This is something in Calc 2, just your basic definite integral, where you had, the integral from A to C was the integral from A to B plus the integral from B to C, right? That you could interrupt it in the middle and just do the different parts. As long as you're only overlapping by one point, where the end point of one is the start point of the next, then these add up just fine. Okay. Now I want to do an example of this fourth thing here, just to show you how that might work. Okay. So I'm going to calculate f dotted with dr over the curve C, where the vector field f of xy, the first component I have is minus y squared plus x, and the y component then would be x minus y. And C is the piecewise linear path from the point 1, 0 to 1, 1, then to 3, 1, and then to 3, 0. So I've got a picture over here. The little blue arrows are the vector field, and the curve that I want starts here at 1, 0, goes up to 0, 1, no, it goes up to 1, 1, and then it moves over to 3, 1, and back down to 3, 0. So, hey, here's editor Will. Looks a lot like, presenter Will. But this is post-recording, and I'm coming back to saying I really wanted at this point to get an idea of what I think this integral is going to be, in that I see along this first curve that at least to start with, the vector field is pointing kind of in the direction that I'm going, right? At least the angle is less than 90 degrees. So I'm gaining some positive value here. Maybe right at the top it might have turned around, but maybe it's still going in the right direction. Okay. So this looks like it should be a net positive along this curve. Likewise, as I'm moving along this curve, the vectors are pointing mostly, to the left there. No, that would be the other left. So that would be to the right. And so again, I'm expecting positive here. So positive, positive. It isn't until the third one here where the vector field starts to go against the flow along that curve. And so along part 3 here, I'm definitely expecting negative contribution here. And maybe even substantially negative, because these are pretty big vectors. And you look at what component of them is in the direction of the curve, so is that big negative going to compensate for those two positives? I can't really tell. It's gonna be close. I don't know who's going to win here, whether the positives are negative, but I'm expecting something. I'm almost expecting negative. I think this is gonna make it negative, but I wouldn't be surprised if it was just barely positive, if close to 0. Anyway, back to your regularly scheduled program. So what I'm going to do is I'm going to break that curve up into 3 pieces. The first piece I'm calling C1, and I'll parameterize it this way. R1 of t is 1 comma t, with t between 0 and 1. So when t is 0, you're here at our start point. When t is 1, you're there at your end point. Now I should point out that each one of these 3 pieces has infinitely many ways that you could parameterize it. And as long as you do it moving from moving in the proper orientation. I wanted to start down here at the bottom and move up to the top. So as long as that's what I'm doing, I'm fine. And I have to make sure I don't double back on myself, but just go down the top, and you could do that any number of ways. So this is not just one way to do this. But pick a parameterization for that first part of the curve. This is the one I'm picking. C2, here's one where there's several reasonable choices to make here. I'm choosing to do along the top edge. The y-coordinate is always 1, so that's easy enough. The x-coordinate I'm going to say is 1 plus 2t, where t is between 0 and 1. So when t is 0, you get a 1 out of that, and when t is 1, you get a 3. Right? So the x-coordinate goes from 1 to 3. I like to set up my parameterizations with t going from 0 to 1. I don't always do it that way, but I quite often do. It just keeps things neat in my own mind. Other people might have done this one and said, hey, let's just call the x-coordinate t, where t goes from 1 to 3. That would be perfectly legitimate. Okay. maybe even easier than what I have here. Okay, so if you see a parameterization that you know is going to cover the curve, then by all means use that parameterization. Make sure though it goes in the right direction. And here's one where you got to be a little careful to make sure it goes in the right direction. So the third part, going from the point 3, 1 down to 3, 0, I'm parameterizing this way, where the x-coordinate is just always 3, and the y-coordinate I have as 1 minus t. Okay. So when t is 0, that's up at 1, and when t is 1, that's down at 0. Now, if you just said, like this first one, if I just said, y equals t, between 0 and 1, then I'd have it oriented the wrong way. It would be oriented upward. Now, I could get away with that and just know that I'm going to have to subtract this, or I need to integrate it backwards, integrate from 1 to 0 rather than from 0 to 1. Again, there's a lot of flexibility you have here as long as you're making sure that your orientations are going in the direction that the curve wanted to go in to begin with. Okay, so now that integral that I wanted to do, this integral here, is equal to the sum of the 3 individual integrals over the 3 parts. Okay, so let's look at each part separately and then add them all together in the end. So first I'm going to do curve 1, and in curve 1, r sub 1 is 1 comma t. So I'm going to need to calculate dr1. So the derivative would be 0, 1 dt. So dr is 0, 1 dt. So f dotted with dr, plugging stuff in. Remember, f was, it's off the screen right now, was minus y squared plus x and x minus y. So the minus y squared plus x, so there's y. So there's the negative t squared plus 1, that's the 1. And then x minus y, so 1 minus t is here. So that's the f with x and y plugged in, but x and y are replaced by what they should be on the curve there. And then I have dr, which is 0, 1. Take that dot product, which is kind of nice with one of those being a 0, so that stuff all goes away, and I just get 1 minus t integrated from 0 to 1. Now, this one I do by the geometry of it, in that I can see the graph of 1 minus t is a straight line that hits the y-intercept, hits the y-axis at 1 and has a slope of negative 1. So for x's between 0 and 1, I'm calculating the area of a triangle with height 1 and width 1, and so the area is a half. So I can just see that that integral is equal to a half. You can do it out if you want, but it's a half. Likewise here, for C2, C2 was parameterized this way, 1 plus 2t for the x component and 1 for the y component. So taking the derivative to get dr, the derivative of the x component here is 2 and the y component is 0 times dt. Now when I do f dotted with dr, I got to be a little careful here because the x's and y's are different. This was supposed to be y squared minus x. No, it was supposed to be y squared plus x for that first part. So the y is 1 here, so minus 1 squared, and then plus x, so plus this 1 plus 2t. And then this was supposed to be x minus y, so 1 plus 2t minus 1. And what happens here? This minus 1 plus 1 is equal to 0, so there's just a 2t here. And you also have a 2t there, so that's just 2t comma 2t. But then when you dot it with 2, 0, the 0 is going to kill off the y component, and you just get 2 times the x component, which is just 4t. So I'm integrating from 0 to 1 of the function 4t. And again, I see this geometrically because y equals 4t is just a line through the origin with slope 4, and from 0 to 1, you move over 1, it goes up 4. So I've got a triangle with a base of 1 and a height of 4. The area is 2. Right, so that integral is equal to 2. And now, part 3. R3 was this, 3 comma 1 minus t. The derivative to get dr, derivative of 3 is 0. The derivative of 1 minus t is minus 1. Again, the f, you got to be plugging in these new x and y's. So negative y squared plus x, there's the negative y squared plus x at 3, and then this was supposed to be x minus y, so there's that. this now becomes, I multiplied this out, distributed the 1 through, added the 3 to get 2 plus 2t minus t squared. And then this is just 2 minus, no, it's 2 plus t, the minus sign distributes in there. So 2 plus t. But then you're dotting with 0 minus 1. And when I take that dot product, of course the 0 times the first part kills that off, and then the 2 plus t times negative 1 is negative 2 minus t. And this I see as, again, it's just a straight line. So at 0, it's at minus 2, and t equals 1 is at minus 3. So I'm looking at the area of a trapezoid, side length 2, other side 3, width 1, and so that has area 2.5, but it's down underneath, and so I got negative 2.5. And so now the whole integral over all of c is the sum of the 3 parts. It's a half plus 2 minus 2.5 for a grand total of 0. So we were wondering ahead of time whether the positives or the negatives are going to win out. It turns out in this just coincidence here that they were exactly the same amount of plus that we gained on those first two, and then it all got canceled out in the end. So the net result is the integral is 0. So there you go. There's one example where you have a piecewise curve where you've got to look at each piece individually, parameterize each piece individually, and then do the individual integrals and add up all the results. There you go. Enjoy.